select the major product that forms from the following series of reactions. So we see that our starting material here is an alkyne. And we should also count the carbon atoms that we have. So we can see we have 1, 2, 3, 4, 5, 6. And no matter which way we numbered this, we'd hit that triple bond at carbon 3. So this is 3-hexyne. And so we want to take it through these series of reactions. So I think it'd be best to draw the product after each reaction step. So if we take an alkyne in the first step, and we treat this with hydrogen gas and Lindlar's catalyst. So this is definitely a hydrogenation condition. We just need to remember what Lindlar's catalyst is. And this is essentially a poisoned palladium catalyst. So like our other palladium hydrogenations, the reaction takes place on the surface of the metal, which means it is a syn addition of hydrogen. So we will have a syn addition of hydrogen. And with an alkyne and this poisoned catalyst, we will see that syn addition appear in the product, because what's going to happen is this will stop at the alkene stage. It's going to stop your reduction from going farther than the alkene. And because it's a syn addition, specifically it's going to stop it at the cis alkene. So you're going to add 2 hydrogens to one side, which is going to push your 2 alkyl groups to the other side. So we're going to draw this alkene. We know the alkene is going to be between carbons 3 and 4, because it's going to be where the alkyne was. So we can draw that alkene. And if we want to, we can take this out of its skeletal structure for a bit to work with. We can see 2 hydrogens on the same side. And then what we have on carbons 3 and 4 as well is just an ethyl group. So we see 2 carbons here and 2 carbons here. Oops, that should be a 2. So this is our cis alkene. Okay. And then in our next step, we're treating this with MCPBA. So what MCPBA is this is a peroxy acid, and it takes your alkene and transforms it into an epoxide. And the stereochemistry here is important. Whatever stereochemistry you had in your alkene, this is a concerted reaction to form the epoxide, and so that stereochemistry remains. So your stereochemistry is conserved in this reaction. And so it's the stereochemistry of the alkene that we're talking about. So in your alkene, your hydrogens are on the same side, your ethyl groups are on the same side. You will see that reflected in the epoxide structure. So you will have your epoxide, and we can say maybe that our hydrogens are both going back, and our ethyl groups are both sticking out at us. Or vice versa. In this case, it's actually a meso compound, so it doesn't matter how we draw it. So we can recognize that as the option here, C. Okay, and the only other epoxide that you might be considering, so this is your cis epoxide. The only other epoxide, and MCPBA might be a good clue for you of an epoxide at this point, is A, and this is a trans epoxide. So we've got 1 ethyl group sticking up and 1 going down. So we could have gotten this product if instead of the hydrogen gas and Lindlar's catalyst, if we took our alkyne and we reduced it with sodium, liquid ammonia, at cold temperatures, -78 degrees C, then we could have gotten the transalkene. Right, and if we did that and treated it with MCPBA, then we could get this trans epoxide that we see in A. But since we did the reduction to the cis alkene, we get the cis epoxide.